Cool. So it's like 11:59. So we're gonna get started like literally on the dot, so that all the speakers get a chance to present their full talk, and everyone gets a chance to ask questions. So people, I guess, will be trickling in as they come in, but we're gonna let Roger from QA get started talking about Yao and Bloqade. And this is a 30-minute talk. So yeah, take it away, Roger.
For this introduction, and hello everyone. Thanks for attending my talk today. I'm Roger Luo, and I'm currently a PhD student from Perimeter Institute, and I'm also a part-time consultant in QR computing. I'm also the author of few Julia packages you might find familiar. So today I will mainly going to talk about the latest development of Yao and Bloqade. I will first give you an update about what we have been working on around the Yao ecosystem, and then we'll introduce you a not so new package which was released last year but haven't presented JuliaCon yet, which is a SDK for QoS neutral atom computers. Then we'll also talk about some of the new features we're working on in towards Yao 2.0. Okay, so in case you haven't seen my talk in JuliaCon 2019, here's a brief review of what this is. So it's a framework for quantum algorithm design and quantum software development. It is written in Julia and has been used in many research projects and also startups. You can check out my talk in JuliaCon 2019. And a few highlights for this package. So we achieved top performance on both CPU and GPU in pure Julia, and compared with all other nice C++ simulators as well. And we're differentiable, so we can differentiate the quantum circuit, get a gradient, and optimize your parameters on the quantum circuit. And we support some basic symbolic calculations through symbolic engines. So what's new in Yao since last time we speak on JuliaCon? So I guess someone mentioned OpenQASM in the morning. So one thing we have is a new package called OpenQASM, also not quite new either. And it provides a pure Julia-based parser for OpenQASM language, and a compiler called Yao.jl that can convert Yao's representation to OpenQASM. This Yao.jl package is actually supported by Unitary Hat, and it's done by R. Sharma. And in order to support and implement all these features for parsing, we not only work on quantum stuff, we actually contribute a whole toolchain for the general Julia community. That includes the pattern matching system, ML style, and the parser generator, RBNF, restricted BNF format. Here is a picture. You can see that we actually parse the string of OpenQASM 2.0, and then we generate the EST. That is why we can provide syntax highlighting in the terminal. The next thing is the ZS calculus. So ZS calculus is a graphic language to help you simplify your quantum circuits, or even you can use it to just reason about your quantum circuit to figure out if what's the variance of your gradient, etc. We developed this package called ZS calculus, which give you an engine to evaluate the ZS calculus based on a given circuit. So here is a demo from the package documentation that shows you a quantum circuit after converted to ZS calculus, and then we can show the corresponding ZS calculus diagram. A work in progress project this summer is aims to also support another version called ZW calculus into this package as well. And this project is led by one of our developer called Chen Zhao, who is also now in QRA computing. This package is still in its early stage, and we're working on integrating with other parts of Yao. And please feel free to try it out and contribute or submit issues. So there are some other features that I won't have time to go into more details. So we have we start to support multi-levels in quantum circuit simulation since last year, and we added more density matrix operations, such as some basic channels, noise channels, and we also have plotting now. And if you want to convert a quantum circuit and simulate using tensor network algorithms, Yao to Ensem allows you to convert Yao's representation to a tensor network representation. And then you can further process the tensor network to get whatever you want. If you're interested in this part, check out Jingguo Liu's talk today on OM Ensem at 4:15. And of course, we have many more small improvements since last time. And worth mentioning, we have this nice package from the community by Zhen, who developed a fermionic linear optics simulator backend for Yao. And it's also located in the same organization if you want to check it out. So next, let me introduce the other package. So we started back in 2020 when the COVID started. We started collaboration with QR Computing and Harvard. And QR Computing is a startup developed start building neutral atom computing devices. And in the collaboration, we start to realize that there are lots of problems in the practice that is relevant to simulating quantum dynamics. And we, based on top of Yao, we start develop this Bloqade package, which is the neutral atom SDK for QRS device. And this was also an exploration for us to expand Yao's scope to more general quantum operators. So what exactly does this package do? So in a simple sentence, it simulates this Hamiltonian. And this Hamiltonian describes the evolution of the so-called Ribber system, which are some cold atoms and can be evolved by some laser beams and then into another state. This is roughly what the machine does as well. So the goal, so this package does a few things, well actually two things. Fast simulation of this Hamiltonian, and that includes exact simulation, simulating set space, and stochastic series expansion, which simulates finite temperature and ground states. And we also support submitting jobs to real hardware. As Catherine talked in the morning, this is actually done through Bloqade. And all these are in one unified interface, of course. So as our tradition, if we want to show a new package in JuliaCon, we need to show it's better than other implementations. So here we go. We have a benchmark with. So we didn't really find any other implementation like this except Qtip in the Python world. So that's why the benchmark here only compare with Qtip. Here, so we compare the Qtip CPU simulation with our both CPU and GPU simulation. The font is probably a little small. I kind of cropped this picture from our documentation. As you can, but you can roughly see that our GPU simulation can be at most 80 times faster than the CPU.
Which color is
Maybe let me make this a little bigger. Oh. Bigger is better, yes. Sorry, bigger is worse. One sec. The top one is time, so the top one bigger is worse. The last two bigger is better. Is the speed up count. So the largest column is the green one, which is the GPU version, and that's and most you can see it's actually 80 times. In the plot, you can probably see it's around 100 for the second simulation. Okay. The other is the Mancala simulation. So this simulator doesn't seem to have any existing implementation and there are some old quantum Mancala simulation in the old package called ALPS, but we don't find any rework, like anything made for rework. This is based on early work from AJS and our intern Anna Knur pushed this into the repo and polished the tutorial. Here is a simple demonstration of the value of the expectation value compared with exact diagonalization. And sorry.
Is this says SSE, is that stochastic?
Yes, a stochastic series expansion. So it's was a kind of quantum Mancala algorithm. The reason why you would want to use this kind of simulator is this kind of simulator allows you to scale to a very large size, such as 20 by 20 lattices. But the limitation is it can only simulate a set of Hamiltonian called sign-free Hamiltonian, and it can only simulate static Hamiltonian in our case. So which is the ground state of our Ripper Hamiltonian in the beginning, or final temperature observables of that Hamiltonian. And also you can connect to real hardware, as Catherine showed you in the morning. So here's a very small code demo that you can submit a very simple pulse program to the real machine located in QRA that has 256 atoms. And of course, we're not actually satisfied with the current performance and accuracy of Bloqade yet. So we're still working on a few improvements. This is including implementation of AC FET solvers, which is currently worked by our intern sitting down there, Kai. So this is his nice plotting comparing. He also works on improving the matrix exponential algorithms. So here's a nice plot from him that's showing that this new method that we pour from NumPy have significantly less calls to the matrix multiplication. And the other thing is a new pulse language so that we can specialize for compilation, also for help you validate your program in the cloud. So, so what's the trick behind all this stuff? There's actually a simple trick behind all these simulation and compilation tasks that is dispatched by some symbolic patterns. And in each package and at each level, we define an expression, describe what the task we want to do, and we usually call them intermediate representations. So from here, you can see for Bloqade expression, that actually defines how the Ripper system works and what needs to be input as your parameter for the Ripper system. And then your blocks actually gives you a general description of quantum operations. For example, you have polys, and you can add them together, and maybe you can want to calculate their commutators. So these operations are defined in your blocks, and from there we can do a bunch of stuff like compile to QASM if it happens to be a quantum circuit, or if this is the Hamiltonian pulse description, we can compile that to JSON schema and then submit the job to QRA, and then run a real hardware. Or if you want to simulate dynamics, we can compile this to a sum of linear operators, which is which you can further put into an ODE solver. And then we can simulate we can run our time evolution simulation primitives. So this does not only allow us to utilize the differential equation ecosystem in Julia, but also allows us to utilize to reuse some simulation primitives from Yao, such as, for example, if your operator is a sum of x or a chronicle of x, you don't actually need to store the whole matrix, and you can directly apply the operator on a state. And we have specialized instructions to implement these kind of operations for you, which is usually faster than just multiply a matrix. And last is our old circuit simulation primitives. And also here I didn't actually draw. If you see Jingguo's talk, you can also convert Yao blocks to OM and some representations, which is a language for tensor networks. And then from there, you can figure out what's the right contraction order for your tensor network simulation. And the main dispatch engine we use here is actually based on Julia's multiple dispatch in the early days, where neither of the developers actually know much about what is pattern matching and functional programming. But with the time growth and we start learning what is more fancy programming tools. So we have ML style, which ports the a functional language called ML family, for example, OCaml. So this port those features into Julia, and then we start to use the pattern match system from ML style, and you'll find some of the expression object actually supports ML style pattern matchers. So this rich system allows us to not just do stats simulation, and we can do many different things by specializing on symbolic patterns. But of course, this does not come for free. So we also learn a lot of lessons when we working around this. So Yao blocks was initially actually not designed for general quantum operations and was mainly designed for quantum circuits. And you'll find it type unstable when you want to manipulate the expression, as John just mentioned in the morning. Now you need some trick to make things type stable. And this will affect the speed of transforming your expression a lot in a Julia program. And also, we don't really have a support for declaring bases, unlike what you have in quantum optics. And the other thing is, when we design our intermediate representation, we didn't really consider the semantics carefully. So it resulted in some redundant semantics, causing ambiguity and bad code reuse. Also, it's not fully it does not fully support pattern matching provided by ML style. So sometimes you might find patterns you expect to work doesn't work, and which is kind of painful for writing complicated transforms. So the solution to solve this would be the Julia 2.0, although we never tagged 1.0, but the API is actually quite stable. For quite a long time, and we're expecting Yao 2.0 to include a major rewrite of Yao blocks and many other improvements, and we hope that we can have a type stable expression to express general quantum operations, and a rewrite of ML style that provides neat syntax for better pattern matching. So this is at least exciting work in progress project to me is an ambitious solution that we try to rewrite Yao blocks with a formalized language, first defined as some BNF syntax, and we have more detailed documentation to define what our each semantic means. And this new language is based on our lessons we learned from Yao blocks and QSpin, and also another failed project some of you might have seen before called Yao compiler. So we realized, in this process, we actually realized the Julia ecosystem is lack of tooling for such applications. So as a start, we actually did some improvement in the journal toolchain. So that includes porting type-stable algebra data type combined with ML style pattern match engine and some improvement to ML style into the Julia. So if you're interested in this part, check out my talk later today at 3 p.m. I guess it's 3 p.m. It's called X-Chronicle. I guess I finished faster than the time should be. So any questions? And also, I guess I don't have enough time to go through all the tutorials. If you're interested in Yao Bloqade, we have a the space is kind of limited, so there are only like first 15 people. So please go to our booth and sign up. Also, lunch is included, if this convinces you. Okay, any questions? I guess.
Thank you for the talk. I was just wondering, did you ever compare the performance of Bloqade with quantum-optics.jl?
Not really, because we find it's so for CPU it should be identical because we're both calling DFQ, unless the matrix are not specialized enough. But that definitely should be like a bonus. And for GPU, we find quantum optics, as far as I know, cannot do GPU. So like, there's no point to compare something not supported.
Yeah, thanks.
So is the intention for the ZX calculus package to be like on par with the Python one and the ROS one, or is it like an experimental thing?
It's more experimental ticket because we want to make use of some other tools, symbolic tools in Julia, such as mana theory, and those two doesn't really exist in Python. We don't cover all the features of physics, but we do get a free speed up compared to physics, like 66 times in some instances. But also the compilation speed doesn't really matter for this calculus.
Have you compared to Quizzix or not?
Not really, because are you talking about Rust?
Yeah, the Rust.
Yeah, so that happens like a bit later when we release to our benchmark release, so we haven't had the time to check that out.
Question back here. You want their hand up? Oh, okay.
You mentioned that in the current version of Yao, there's something lacking compared to quantum optics, defining arbitrary basis. That's actually the use case that was kind of important for me when deciding between those two tools. I really need something that can do more than just qubits. Could you elaborate on what the plans there are? What will be the near-term capabilities for analog, non-qubit physics?
Oh, yes. So the near-term So near-term plan is to, in order to actually define these formal languages, we need a good way to define an abstract syntax tree. So my near-term spare time will be mainly improve the tooling first, and then in terms of the actual support of the bases, I think within the language, within this language design, this is kind of easy to support because we already figured out the corresponding semantics. But in terms of, but based on that, some further developments will include, for example, generate matrix from the expression, or just generate one entry given the basis. So these are more important to the actual simulators. I don't really have a detailed plan for those, but we did consider these use cases.
Thank you.
We got other questions? Anybody? We still have a few minutes, so if someone has another question.
Can you say, or yeah, maybe I should take this. I got a booming voice anyway, but sometimes I'm told. I'm wondering about what a little bit about these representations that you use pattern matching on and so forth. And you talk about this as a solution to a certain extent to a dispatch system, but I'm having, it's a little fuzzy to me. Are these like expression trees? That you rolled your own expression tree and send those around, or?
Yes, for some of the representations, they're essentially just a syntax tree of some language we defined. And this is not true for Zest calculus and some other graph-based representations. So those representations are graphs, and we currently do not touch general graph matching. We do, in order to implement Zest calculus, we do implemented some naive pattern matchers for the graphs.
I see. So these you'll have like a syntax tree, and in order to recognize, rather than go through that in a detailed way with if-else statements, you'll use something like an else style.
Yes.
Thanks.
Okay, we probably have time for one more. If anybody has any last questions? If not, let's thank our speaker. Oh, sorry, actually.
If that's still
Yeah.
I just wanted to ask, you mentioned in Bloqade a representation of pulse information. Can you describe that representation a little bit? Is it related at all to like open pulse, or is it something completely different?
It's something more specialized to the machine, so it's not open pulse. It's because the pulse program on US machine is actually simpler than what open pulse describes. So we want to remove some redundant semantics, so things get simpler.
Okay, so it's more specialized.
Yeah.
Thanks.
Cool. So let's thank Roger again for the great talk.